Okay, so hello everyone. I am Bittu Singh. I'll be teaching. That is, I am a TA of this course. So first, this is our first class. Here we solve some problem on those following topics. That is matrix calculation based on matrix and row reduction or row echelon form, row reduced echelon form. Solving linear equations. And we know we'll learn about vector spaces. So this is our goals. Okay, there are three peoples. Okay, so start. Here you can see that the given matrix is A, and you can see that A is of this form here, and we'll apply some row reduction. So P denote the elementary matrix which replaces row 2 by row 2 minus 2 times row 1, and row 3 by row 3 minus minus row 1. Then what will be the value of P? So let us see how to solve this problem. So we are applying row reduction. Now if we assume I equal to identity matrix corresponding I, it will look like 1 0 0 0 0. Sorry. So we can see it is 4 by 5 matrix. So row reduction means we are multiplying some elementary matrices in this on the left side. So it should be 4 by 4 matrix, and it comes from identity matrix. So the 4 by 4 matrix identity will look like 1 0 1 0 0 0 0 1 0, and the last entry will be 0 0 0 1. So what are we doing? First, replace row 2 by, so R2 is replaced by R2 minus 2 times R1. Okay. So first row is unchanged, 1 triple 0, and second row is R2 minus 2 times R1. So 0 minus 2, it will be minus 2. After that everything is 0. So multiplying 2 will give 0, and just subtract from 1 double 0. This 1 double 0. So it will become 1 double 0 again. What will be the third element, third row? So third row is given by row 3 minus row 1, that is R3 minus R1. So if we apply this process, this is row 3 and this is row 1, just subtract row 1 from row 3. So what will be the value? So 0 minus 1, 0 minus 1, it will be minus 1. After that, all are fixed because all those things are 0 in row 1. So it will become this. Sorry, there is 1. So corresponding 1. After that, everything is 0. Okay. Yes. Hello. Are you saying something? Okay. And again, fourth row will be unchanged. So this should be the result. This should be the answer. So we can see that minus 2 minus 1, it should start with minus 2 minus 1. What is the answer? this should be the answer, right? Everything is matched. 1 triple 0 minus 2 1 double 0 minus 1 0 1 1 0. So this is the answer. So here the answer will be answer D. Next, here we'll consider the matrix from the question 1, and the matrix B. Here some options are given. Now we need to check if B is row equivalent to A. So how do we see some matrix? One matrix is row equivalent to another. So given a matrix A, so B is said to be row equivalent to A if B is obtained by. Hello? Hello? Is there any problem? Hello? Okay. Can anyone confirm if it is okay or not? Okay. So continue. So we are getting a matrix B which is row equivalent to A. So the meaning of this is we are applying some elementary row operation, that is we can subtract. So we can subtract like this. So row 2 minus some constant time row 1, those type of operation is allowed. For example, row 2 minus 3 row 1. And what are other possible operations? We can multiply with any row. So for example, row 4, this row 4 can be multiplied with 5. Or what are the other possible operations? We can exchange any two rows. For example, these two rows are exchanged. So row 2 and row 3 can be exchanged. We may, maybe this is a better notation, exchange those two rows. So applying all those type of operations, if we get a matrix, suppose some matrix B, then B is said to be row equivalent to A. B is row equivalent to A. So what are all possible operations? We can scale any row. So here we can maybe row 4. Here we can multiply this row 4 by 5. We can exchange those two rows. So this row can be written here and this row write it above. So we can do such operations. And what is the last possibility? We can subtract one row from another by some scaling factor. So for example, we can subtract this row 1 from row 2. So row 2 minus 3 times row 1. Those are the all possible operations. So let me see if this B can be obtained from A. So recall that A, given A was 14010. So I'm copying that question. 14010. Then 210 minus 10. After that 18020. And next last row is 01201. 01201. So from here you can see after first row all leading entries are 0. Here 0 0 0. All the answer contains zeros after first row. So what we can do to make row 2 first entry or leading entry to vanish, make it vanish, what we can do, row 2 minus that is subtract 2 times row 1. So 14010 first row is unchanged. Now subtraction give 0, then 1 minus 8, it will be minus 7, then 0 again, -1, -2, that is -3 and 0. Similarly, subtract, that is R3 minus apply R1. R3 minus R1, it will give you 0, then 8 minus 4. This will be 4. 0 minus 0, it will be 0. 2 minus 1, 1. After that, it is 0. And 0, 1, 2, 0, 1. Let me check if any of the answer matches with our calculation. So, what are the possibility? First answer, the second row is 0, minus 7, 0, 3. So here the sign is changed. So first answer, first option cannot be possible. Now, if we see the second answer, -7, -3, this is matching. 4010, it is also matching, but 1302, so it is not matching. So this is also not, this may not be true. Now, 0 minus -7, 0 minus 3, maybe this 4010, 1201. Okay, so we can see that answer C. So option C is matching. Therefore, B, the answer is B is row equivalent to A. This is true for option C. Okay. So let us see the next question. Here, row echelon form of a matrix A. So what is row echelon form? Row echelon form is obtained by such operations. So suppose A is a given matrix. What we can do, again, we will do some row reduction. That is all three possible operations: scaling, row exchanging, or subtract one row from another by some scaling and subtract. So those are all possible operations. But row echelon form will take a particular form. It is some kind of diagonalization, though, because it is, for example, here we can see this is 4 by 5 matrix. So for 4 by 5 matrix, diagonalization is not possible, because, or triangulation, that is, it is not completely a symmetric triangle, right? So what we can do best, we can do some row operations, and we'll reduce into like this. So one row. So let us see what are the all possible 2 by 2 row echelon form. For example, you can see that 1, 2, 3, 4. So suppose A is a matrix like this. So what can we do? We try to make it diagonal. Not diagonal, we will try to make it upper triangular matrix, which is not always possible. But what can we do best? What can we do optimal way, in an optimal way? So we can subtract 1, 2, and subtract 3, 3 times row 1, and it will be 4 minus 6. So it will be -2. So here diagonalization means triangulation, upper triangulation is possible, but it is not always the case. Okay, so what we can do, just subtract, that is, first leading entry should be 0. First, sorry, suppose this is a leading entry, and after that everything should be 0. Okay, for example, row 2, row 3, row 4, those are 0. Then again, you can see that leading entry of second row, it is -7, which is just after the first column. Then after that, all should be 0. Okay. Again, for third row, you can see that it start with third column. Below that, everything is 0. Okay, so this is called row echelon form. Now we are again doing row operation. So previously we obtained this answer. Let me copy. Okay. Okay. So after some row operation, we get this. Now again we'll do some row operation. So what will be the next step? Next step is to reduce, that is cancel those 4 and 1, because after -7 it should not contain any non-trivial non-zero element. 1 4 0 1 0, first row is unchanged, second row is also unchanged, 0 -7 0 -3 0, and after that how to cancel this? So what will subtract to cancel 4? What we can do? We just subtract R3 minus, that is plus 4 by 7 times R2. Then we can see that 4 will get cancelled, right? So it will become 0 0, and 0 plus 4 by 7 times 0, which is again 0. 1 by, that is next entry is 1 minus 3 into 4 by 7. So again, if we calculate, it will be minus 5 by 7. Next entry is 0. Again, what can be done for the last row? We'll perform R4. We want to cancel this 1, right? So what can be done? Just multiply 1 by 7 with R2 and add 1 by 7 times R2. If we do this, we'll get 0 0. 2 is fixed because of 0 above, but here 0 minus 3 by 7, and it is fixed 1. Now again we can see that row 3 contains this non-trivial element, non-zero element, so below that everything should be 0. Therefore we need to cancel this minus 3 by 7. So again apply row operation, we'll get okay, is it correct? 1 2 3 4. Okay. Sorry. First non-zero element is 2. We cannot cancel 2, so we need row exchange, because so we need to do this row exchange. Row 3, row 5, 4 will be exchanged. It becomes 1 4 0 1 0, 0 minus 7 0 minus 3 0. Then row 3 row 4 are exchanged, so it will become 0 2 minus 3 by 7 1 0, and after that 0 0 0 minus 5 by 7 1. So you can see that below minus 5 by 7 there is nothing, therefore it will be the row echelon form. Let us check if it is matching with those options. So you can see first should be 0 minus 7. It is given for all answers. So third row should be 2 minus 3 by 7. 2 minus 3 by 7, it is there. 2 minus 3 by 7, 1, then 0. 2, sorry, what happened? It should be, sorry, 0 0 2 minus 3 by 7 1. Sorry, just copy the. So 0 0 2 minus 3 by 7 1. This is also present. Minus 5 by 7. Here it is 0, but you can see there should be some 1. Right. Sorry, it is not 1. It is actually 0. Okay. So it matches with which option? It matches 0 0 2 minus 3 by 7 1 minus 5 by 7 0. it matches with option A. Is it -7, -3? Okay, it matches with option A. So the correct answer should be option A. Right. Okay. Okay. So let us see the next question. Now we need to do row reduced echelon form. So for row reduced echelon form, it is again we apply some row operation to the row reduced, that is row echelon form, and we try to obtain some identity or diagonal matrix. But again, it is not possible because it may be 5 by 4 matrices, and it may contain some zero rows. So obtaining identity or diagonal matrix is not always possible. So the question is, what can we do the most efficient? How can you make the most efficient matrix out of this? So what we can do, we will again perform some row operation. So it's top here. Now we'll again apply some row operation to reduce it further. And what we'll do, we can see that above 2 here it does not contain anything, but above -5/7 it contains some element. So we want to cancel those elements. And another thing is that leading entry, this should be 1. For example, here it is -7, then we need to divide it by -7 so that it becomes 1. Okay, and again there is something before the leading entry, there is something above the leading entry, it need to be cancelled. So we need subtraction. Let us do those operations. So just to make leading entries 1, we can perform 1/7 times row 2. Similarly, half times row 3. And -5/7. Before that, let us perform this operation so that it will easily reduce. So it 7 by -7/5 times row 4. If we do this operation, then last row will be 0 0 0 1 0. Now if we multiply with some number and we just add or subtract with above rows, then we can see we can easily make the above element, make it vanishes, right? So it will become 1 4 0 0 0 0 -7 0 0 0 and 0 0 2 -3/7 is 0 and 1 remain 1. So how do we get such thing where we are adding and subtracting? For example, if we get 1 here, then what we can do, we are obtain. So after that we are again multiplying and subtracting. For example, here when we are getting 1, just multiply 7/3 with this row R4 and add with third row. Then we can see that this element will be cancelled. That's why we are getting 0. Similarly, what we are doing, again multiply with 3 and add with second row. That is, second row is actually R2 times 3 R1. Similarly, we are subtracting from R1. So R1 minus R4. So we have not written the intermediate step because it is not necessary. Just apply this operation so that we are getting this matrix. Now again we can see that if we multiply half with row 3, then this matrix will change to 1 and here it will becomes half. Therefore, by the same process, so here the above entries are zeros, so it is okay. What can we do again? This second row, just multiply with -1/7 with second row. Therefore, it will -7 will becomes 1 and all those will be 0, 0, zeros. Okay, it is okay. Now, what will be the last step? So, to cancel this 4, we do this operation R1 minus 4 times row 2. Therefore, it will becomes 1, 0, 0, 0, 0. And after that 0, 1, 0, 0, 0, 0, 0, 1, 0, half, 0, 0, 0, 1, 0. So now we can see that leading entries are 1. All the leading entries in every row, those are 1. And what can be seen? That above leading entries, all those elements are 0, right? Above and below. So now we cannot reduce it further. So here we'll stop. Okay, so let me check if it matches with those options. So you can see this is 1, 0, half, and yes, it is, but it contains 1 here above, so it cannot be possible. 0, it is again not possible, it is not half, so this is also not true. So D, option D is the correct answer because we can see every entries are matching. And you can note that row reduced echelon matrix for any given matrix, it is always unique. Okay, though row reduction and row echelon matrix, there can be many possibilities because we can do many other operations also. Okay, we'll get similar kind of row. For example, 1, 2, 0, 1. This is also a row echelon matrix, but if we subtract 1, 0, 0, 1, this will be also a row echelon matrix corresponding to this A. But when we are saying row reduced echelon form, this is unique because above this one everything should be 0. So what if you do any operations, you will get unique row reduced echelon matrix. Okay, so here you can see that option D is the correct answer. Okay, let us solve the question number 5. The question is A equal to this. Now A is obtained. Sorry, this is just cancel this line. This is, so the question is x equal to this and y equal to this. So again cancel this line x. So y is y1, y2, y3, y4, this column matrix. So the question is then ax equal to y. If ax equal to y has a solution, what will be the condition between those, among those y1, y2, y3, y4? So let us rewrite the question. We need to solve x equal to y. So not we are not solving, but y is given tuple like y1, y2, y3, y4. Now what is the condition so that this matrix equation has a solution? So let us write in this form. So a is 1 minus 2 0 0 1, 3 minus 6 2 0 7, minus 3 6, minus 2 1, minus 4, and the last thing is minus 2 4 0 0 minus 2. This, and x is x1 x2 x3 x4, and y is this equal to y1 y2 y3 y4. So to solve those kind of question, what we'll do, we'll provide augmented matrix corresponding to the equation. So how can you make augmented matrix? Just put A and put this Y transpose. So this is Y transpose. So put Y transpose here. Maybe Y transpose. Okay. If we put like this, then what we are getting, we'll copy. Okay. So this is A and Y is Y1, Y2, Y3, Y4. Is it matching with the previous questions? No, this is different question. Okay. Then we'll perform row operations. So what are the row operations? We can subtract 3 times R1 from R2 so that these 3 get cancelled. Sorry. Similarly, we can add 3 times this R1 so that R3, row 3, this leading entry vanishes. And similarly, row 4 plus 2 times row 1 so that these 2 get cancelled, right? So let us do those operations. So first R2 minus 3 times row 1. 1 minus 2, 0, 0, 1. This is Y1. Then R2 minus 3 times R1. This becomes 0. Minus 6 plus 6. This will be 0. 2, 0, 7 minus 3, which is 4. And Y2 minus 3 times Y1. Similarly, apply R3 plus 3R1 so that this leading entry becomes 0. 6 plus 6, sorry, 6 minus 6, it is again 0. Then minus 2, 1, and minus 4 plus 3. Minus 4 plus 3 means minus 1, right? And this will be Y3 plus 3 times Y1. Now, same thing, R4 plus 2 times row 1. So it will get 0, and 4 minus 4, it is again 0, then 0, 0, and minus 2 plus 2, it is 0, right? But here we are getting Y4 plus 2 times Y1. Now you can see that if this is non-zero element, suppose this is 3. So we are, from this equation, we are getting equivalent equation, but here the left side is 0 and right side is 3. So 0 equal to 3. For we are considering the last equation. So what is the last equation? Last equation is 0 times x1 plus, yes, plus 0 times x2 plus 0 times x3 plus 0 times x4 plus 0 times x5. This equal to y4 plus 2y1. But what is the meaning of this? This is same as 0 equal to y4 plus 2y1. So if y4 plus 2y1 is some non-zero element, then this equation has no meaning, because we cannot say 0 equal to 1. This is not true, right? Therefore, this element y4 plus 2y1, this must be 0. Otherwise, there is no solution. So what is the possible answer? So this should be 0. This is equivalent to saying y4 equal to minus 2 times y1. Therefore, this should be the right answer. Y4 is equal to minus 2 times y1. Okay. Sorry. So this should be, x is there. Okay. Is there any doubt up to this? Okay. Okay. Please. Okay. Please go ahead.
Sir, if there are two rows, we are getting all elements are zero, then what will be the answer?
Okay. You are saying if any other we are getting something 0 on the left side and non-zero on the right side, like this.
No, sir. Suppose we are getting two rows in which all
Yes.
the elements are zero. Suppose
Yes.
y2 minus 2 y1, and another row is also there, y4 minus something y1 is equal to 0. So in that case, what is the correct answer?
Okay, then there should be two different. There we need to make two different choices, two different relation. Not only this, but there can be another relations. So actually, this is not stopped here. So let me do another step. So it is up to now. It is not a row reduced form, row echelon form. So we need to make row echelon form. Okay, so
Okay,
that
sir.
we can say something.
Okay,
So
sir.
for row echelon form, what can be done next? So just to cancel this thing, we just add row 2, right? So there is no space. So let me write here. So we'll do R3 plus row 2, row 3 plus row 2. So above that everything is same, but now row 3 will be changed. So it is 0, 0 minus 2 plus 2. So it becomes 0, 1 0 plus 0. It is 1 minus 1 plus 4. This is minus 3. And here everything is fixed, but that element will be y3 plus 3y1 plus y2 minus 3y1. Right? So it is same as y2 plus y3, the addition. And the last element is 0 and the same thing. So now you can see that all those three rows are linearly independent. So there is no such relations. The only relation occur here. Okay. If you do row echelon, if you make it row echelon form, then you can obtain what are such relations. Okay. After that you can conclude, because now no relation can be made. Okay. Please say okay. Surendra Srivastav. Yes, please go ahead. Uh, what is the problem? Hello, Surendra. Is there any doubt? Maybe it is mistakenly. Okay. So let us solve the last problem. So here P3x, it is vector space of polynomial of degree less or equal to 3 over real number. So you know what is polynomial vector space, right? So P3x, this will contains elements of this form. It will be A0 plus A1x, that is vector space which contains degree 3 polynomial, plus A3x cube. And what are the coefficients? Coefficients should come from real numbers. So P3x will look like this. All such polynomials up to degree 3, and coefficient, because it is vector space over real number. So coefficients are from real numbers. So this will be the P3x. Now what is the questions? W be a subspace of P3x consisting of elements like this. So I have written that. Now then Px can take the form. So we have chosen Px from W. So what can be a suitable form for the polynomial Px? So here, so let me write explicitly. So corresponding to the first option, W is given like this. W is all P3x from, sorry, it is Px, all Px from this polynomial space P3x, such that first coefficient A0, okay, I have written in a opposite order. So let me rewrite it. A0, A1, A2, and this is A3. Okay. Well, A0 is given as A0 greater equal to 0. So is it possible? Will it form a vector space? So 0 belongs to W. Is it clear why 0 belongs to W? Because 0 plus 0x plus 0x square plus 0x cube, this satisfies the condition A0 greater equal to 0. It is satisfying the condition. So 0 is there. So 0 vector is present. What are the all possible conditions for a subspace? So we know to check if something is subspace or not, we need to check these two conditions. If V and W, first we'll check if 0 belongs to the subspace W or not. We'll start with these conditions, though it is not necessary, but it is easy to discard by this reasoning. That's why we'll always check this condition. Next, second thing we'll check if V1 and V2, suppose two vectors are there, W, we need to check if V1 plus V2 is there. So suppose those two are holding, then will it be vector space? Will it be a subspace of V? No. What can be checked? The last condition should be if V is there, V is in the W, then we need to see all scalar multiplication. If we scale some vector, it should also belongs to the subspace W. Then we'll call it a subspace. So W, which is a subset of a vector space V, it is said to be subspace if addition, it is closed under addition and closed under scalar multiplication. Then we will call it W. It is a subspace of V. Okay. So CB should be belongs to W. So those are the conditions we need to check. So here 0 is there is no problem. But if we the second condition is also holding, if something is greater equal to 0 and add with another thing which is also greater equal to 0, then their addition will be greater equal to 0, right? So second is also holding, but the last condition, if we multiply some, so here if you see for this question, that for option A, we are checking option A. Here you can see that if you take A0 to be plus 1 and everything other thing to be 0, then you can see xs cube, that is 1 times xs cube, belongs to w, right? But if you multiply -1, choose c equal to -1. So this is px equal to xs cube. Now choose c equal to -1 and multiply with this vector p. Then minus c times px, this will be -1 times xs cube, right? Which is minus xs cube. Now you can see that this coefficient a0, this coefficient of xs cube, this is negative, which violate the condition. So from here we can conclude that those one vector is present in W, but their scalar multiplication, if we stretch the vector, it does not lie inside W. Therefore, it is wrong. It cannot be the answer. Okay. So let me check the second option. So here A2 is same as I times A1. That is, this entry is same as I times this coefficient. So for example, if you choose A2 to be I and A1 to be 1, that is, take this polynomial ix plus 1 times x square, and everything is 0. That is 0 plus ix square plus 0 x cube. So it belongs to this space, right? This belongs to this space, this satisfying the condition. But what is the problem? This element cannot lie inside the vector space V itself. So this W cannot be a subspace of V, even subset of V. W is not even a subset of V because it contains some complex coefficient, which is not possible, right? It is already given real coefficients. So any subset of this thing should always contain real coefficient. Therefore, it also cannot be possible. Let me check this condition. If A3 is rational, so A3 is rational. If you write this, A3 is rational, so we can take this element, right? So A3 is rational, A3 is here. So, for example, rational number, what is your favorite number? Rational number, let us choose 1 plus x cube. So consider this polynomial. So this belongs to, here let us rename it as W3. This is W1, this is W2, and this is W3. W2 violates this condition. Now W3, so for W3, it belongs to W3, but it is vectors, it should be subspace of real number. So C should be a scalar field, C should be an element of scalar field. So here scalar field is real number. So take your favorite real number. For example, you can choose pi. Pi belongs to real. So this is scalar, this is your given vector V. Now multiply C with V, then you will get pi plus pi x cube, right? Now you can see that coefficient of A3, it is now not a rational number, but it is given that coefficient of A3 should be rational. So again, it violates condition. Therefore, this is also not possible because it is not closed under scalar multiplication. So it is not closed under scalar multiplication. It is again not closed under scalar multiplication, and for here it is not even a subset. So those are the defects. Now for option C, it is true. Why it is true? it is given that A3 is same as A1 plus alpha square A2. So let me erase those things. Okay, I am not erasing. Let me write somewhere else. Okay. Here A3 is given as A3 is same as A1 plus alpha square A2. A3 is same as A1 plus alpha square A2. Alpha is a real number. So A0 x cube, A1 x cube squared, A2 x plus A3. Suppose this is P1 and similarly let me write it as P and similarly P dash x. This is A0 dash x cube plus A1 dash x square plus A2 dash x plus A3 dash, such that those conditions are holding. That is A3 is same as this. So let me copy. Such that, and similarly this such that A3 dash also satisfies this rule. A1 dash plus alpha square A2 dash. So first we can see that 0 is already there, because if we write 0x cube plus 0x square plus 0x plus 0, this polynomial, so this is the polynomials, let us write it as 0x. If this is the polynomial, then we can see that third entry, which is 0, this satisfies the condition 0 1 2 3 0 1 2 3, sorry, third entry is this. So third 0, it satisfies A1, which is 0, plus alpha square A2 plus alpha square A2 is again 0. So 0 belongs to W3, it is clear. Now if Px and P dash x, those two belongs to W3, then we need to check if P and P dash, their sum also belongs to W3. But is it true? So what will be the sum of Px plus P dash x? The sum will look like A0 plus A0 dash x cube, A1 plus A1 dash x square, A2 plus A2 dash x, A3 plus A3 dash. Right? Now we need to check what? We need to check that the last entry, which is A3 plus A3 dash, if this is same as, we need to check this, if this is same as A1 dash plus alpha square A2 dash. Here A1 dash is this, that is first element, A1 plus A1 dash. And what is the second thing? Second thing is this. So plus alpha square A2 plus A2 dash. Is it true? Is it true? Can anyone say if it is true or not? So just add those two equations. From here we can see A3 plus A3 dash. This is same as A1 plus A1 dash plus alpha square A2 plus A2 dash. So from here it is clear that it should be true. Therefore, it is true. Hence, W3 is closed under addition. What will be the last step? Last step, we need to check if we multiply with some real number, suppose C be a real number, then we need to see that C times Px, this is also an element of W3. But it is also true. Why? Because if Px belongs to W3, Px belongs to W3, then if we multiply then it c times px, this is same as ca0 x cube plus ca1 x square plus ca2x plus ca3. But here we can see that the last element, which is ca3, this is same as a1, means first element, which is ca1, and alpha square times ca2. This is also true because of this, right? From here, just multiply with c, then we'll get this equation. Okay, therefore it is closed under scalar multiplication. Hence, we can say that W3 is a subspace. Okay, so here we are done. So let us see the question number 7. So in question 7, we need to check if those options are correct or not. Which statement is correct? So the first question is, V is vector space of n by n matrices over a field F. So V will look like set of all n by n matrices. Okay. The solution space of a system of homogeneous linear equation may not form a subspace of Fn cross 1. So let W is the subspace of this form. So W is given as all matrices A belongs to Mn cross n, all n by n matrices, which satisfies the equation, this homogeneous equation, Ax equal to 0. So it is said, it says that this cannot form a subspace. This is not a vector space. This W, this subspace is not, this subset is not a vector space. So is it true or not? So it is obvious that 0 is there because A times 0 is always 0. So 0 belongs to W. Zero belongs to W. Maybe write it as W1 because there are several options. Now suppose x1 and x2, those two are element of W, and C is any scalar of the field F. So instead of writing separately, we may just check these conditions. This condition, that is C times x1. So v1, v2 belongs to W. It is enough to check cv1 plus v2 also an element of W. If this is hold, this is true. So W is a subset of V such that this implies this, and C is element from scalar field F. Then the conclusion is W is subspace of V. So it is enough to check Cx1 plus x2. This is also belongs to W. W1. We need to check this. So is it true? Let us check. So to check if something belongs to W or W1 or not, what we will do? We need to check if this equation satisfied. So A times Cx1 plus x2, it can be written as C times Ax1. C is any scalar, right? Small c, plus A times x2. But we have assumed that x1, x2 both belongs to W. Therefore, Ax1 is 0 and Ax2 is also 0. Hence, this is actually C times 0 plus 0, which is same as 0. Therefore, it is true that W1 is subspace of V. Subspace. So this is true. Therefore, it cannot be possible. Next, let us check the second option. So here you can see that it is a subset is given by n tuples such that A1 is 1 plus A3. So n tuples should satisfy this condition. So will it form a subspace of Fn? Fn means n tuples which comes from the field F, given field F. So will it form a subspace? Can anyone say if it is true or not? Yeah.
Sir,
Yes.
sir, tuple means what, sir? How we can understand?
Okay. N tuples mean it will be pair of this form. For example, if you write R2, this is R2, right? In picture, then any element, for example, this is 1, 2, 3, 1, 2. So we can represent element of this form, x comma y, this pair. So it is said to be two tuples.
Okay.
Similarly, for 3D, we need three pairs. So x, y, z. This is said to be three tuples. Okay.
Thank you, sir.
So can you say if it is forming a subspace or not? So first thing should be first thing we need to see if 0 belongs to this n tuples. That is, if you check the 0 element of this Fn, it will look like 0, 0, 0 everywhere. So here the third piece is also A3 equal to 0, and A1, this is A1, first element, A1 is also 0. So is it satisfying the condition A1 equal to 1 plus A3? So from here you can see 0 does not belong to the subspace, because third element there should be relation that A1 should be same as 1 plus A3. So 0 vector does not satisfy this condition. Okay, so this cannot be an answer. So let us check the condition C and D. So here you can see the n tuples 0 is already there, because 0 satisfies the condition A1 equal to 0. Here you can see A1 is 0. For the 0 vector, A1 is 0. Therefore, it satisfies the condition, given condition. Now, what do we need to check? If this subspace, so denote it by W3. Third option, so we are denoting by W3. So is it satisfying the condition? That is it closed under scalar multiplication and addition? Let us check. So it is question number 7. I think it was 6. So question number 7. Option C. Here W3 is given, the subset is given as A0, sorry, not A0, A1, A2, n tuples of Fn. Fn means set of all those n tuples. And how do you add those n tuples? Just add pointwise. Okay. For example, 2, 3. Let us consider these two tuples. 4, 6. Just add first two element, add second two element. So addition will look like 6, comma 3 plus 6, which is 9. Okay. Similarly, how do you multiply? What will be scalar multiplication? So, for example, consider that 2, 3, and let us multiply it by 3. That is scaling by the factor 3. So it will becomes 6 times 3 into 2, 3 into 3. 6 times 9. Those are some examples. So the condition was that it is a subset, it comes from Fn in tuples, but it additionally satisfies the condition A1 equal to 0. So to check if something is subspace or not, what do? We check the condition. First condition will be like this, that 0 is already there, but let this vector v, which is same as a1 a2 dot an, and another vector maybe v1, this is another vector v2, or let it w, which is same as b1 b2, another intervals. So vw, those belongs to w3. What is the meaning of that? That a, this belongs to w3 means a1 should be 0, or we just put 0 here. A1 is 0 means first entry is 0. Similarly, W is belongs to W3. What is the meaning of this? This means the first entry is 0. This is the condition. So those two elements are from W3. We need to check. So C is an element from the scalar field F, maybe this F. Then we need to check if CV times W, this is also an element of the W3. So what will be CV plus W? So we need to check this condition. You can see that CV means 0 plus 0 comma CA2, multiply each entries with C, and the last element becomes CA plus W. W means 0, B2 up to Bn, right? Then add those two things. Adding means pointwise, add pointwise. So first element is 0 plus 0, which is same as 0. Second element will be Ca2 plus B2. So it is Ca2 plus B2 dot dot. Last element will be Can plus this Bn. Can plus Bn. So you can see that here the first entry is 0. Right? So first entry of Cv plus W is 0. This implies Cv plus W belongs to W3. So this is true. So therefore W3 is a subspace. So this is the condition which we will check. That is, it is closed under scalar multiplication, C times B is there, and closed under additions, V plus W is also there. So this is holding in this case. Therefore, it is true that this answer is true. That is, n tuples such that A1 is 0, it belongs to this. It is forming a subspace. So this forms a subspace. This is true. Let us check the last answer. Here we are considering the set of all Hermitian matrices of Hermitian n by n matrices over C, which is over C with respect to standard addition and scalar multiplication. Okay. So for option D, here the option D, this is let us denoted by W4. It is all complex n by n matrices. So This is subspace of all n by n matrices over C with respect to standard addition and scalar multiplication. Okay. So W4 is given by this. So it is set of all n by n matrices. It will contains those n by n matrices and entries. Those entries comes from C. So W4, those matrices will be n by n matrices whose entries are from C, and it is Hermitian. What is the definition of Hermitian matrix? Hermitian means A node is same as A. This is A node means it is actually, the definition is take conjugation and do the transpose. So maybe we can denote it by A bar transpose. Okay. So what is the meaning of A bar transpose? Let us just do a quick example. For example, 1i 2 3, is it Hermitian or not? So let us check if it is Hermitian or not. So what will be A bar? This is A, then A bar is same as, just apply conjugation. For example, let us denote it by, let us do 2 plus I. Then what is conjugation? Conjugation means A plus IB, replace A plus IB by A minus IB, right? So 1 becomes 1. So here it is 0 plus I, therefore it becomes 0 minus I, that is minus I. Here it will be 2 minus I, here it will be 3. But again we need to do transpose. So A naught, it is given by transpose of A bar, which is same as 1 minus I. First row becomes first column and second row becomes second column. 2 minus I, 3. So this is the conjugation and transpose. So will it, so from here it is clear that A naught and A, those two are not equal, right? So in this example, A cannot be Hermitian. A is not Hermitian matrix. This is just for example purpose. So let us solve this problem. Here you can see that W4 is of this form. We need to check if W4 is closed under scalar multiplication and addition. First question is if zero matrix is there or not. So zero matrix will be like this: 0 0, everywhere is 0. So it already belongs to W4, right? So we cannot discard. We need to check that scalar addition and multiplication is also there. So this is inside W4 because all zeros, those entries are complex number already, because real number is also a complex number. So this is already there. And if you do conjugation, because all entries are real, conjugation will be same. And again, this is symmetric, therefore transpose will be again the same thing. So this is inside W4. Now suppose A and B, this belongs to W4. And this scalar K, it comes from the complex field C. So we need to check the addition A plus B is there. Need to check this. And the second thing is C times A is there. So we have already said that checking those two things are equivalent to checking CA plus B belongs to W4. This is equivalent. So we can check one of the thing whenever which is easier for you, just check any of these conditions. So here it is not C, so let us denote it by maybe K, replaced C by K. Okay, so if A and B not satisfy these conditions, that is if A and B belongs to W4, means A not equal to A and B not equal to B, then you can easily verify that A plus B naught, this should be same as A naught plus B naught. It is easy to check because just apply conjugation and do transpose. Okay, you can easily check this is true. It is same as applying individually and add. So this is true. Now, so closed under addition is clear. Now, if this is closed under scalar multiplication, that is K times A naught, if this is same as K times A naught, will it be true or not? So let us check. So, for example, can you give me one element from A naught? Maybe 1, 0, 0, 1. This identity belongs to W4 because this is Hermitian matrix. Do conjugation of this thing. A bar, this is same as identity matrix, and instead of n by n, we are just considering 2 by 2 for our purpose. And let us choose K to be I. Then, so suppose this is A. Then what is K times A? K times A is same as I, 0, 0, and I. Now what is Ka bar? Ka naught. So it is A naught equal to A, it is clear. But what is Ka naught? Ka naught means we take conjugation and we'll transpose. So conjugation means -1, 0, 0, minus I, and take the transpose, which is same as, by symmetry it is clear transpose will be same. Row and just row is become column and column becomes row. So it is same as this. But A naught is identity matrix. A naught is same as A, which is identity. But you can see that K times A naught. What is K times A naught? K times A naught, it is same as A naught was 1, 0, 0, 1. But K is this I. That is K times A naught is same as I, 0, 0. So from here you can see that K times A naught, this is not same as K A naught. So the last condition is violating, right? Is it clear? So this is not true. So this equality is not always true. That is not true for all K belongs to C and A belongs to W3. So this is not true. One example will be like this. We have considered a particular case, 2 by 2 matrices, which are Hermitian. But we can see that K A naught, this is not same as K times A naught. That is scalar multiplication is not there. Is it okay? sorry, k times a naught, sorry, k times a naught, it should be same as k. K. This is a mistake, big mistake, because we need to check if k is Hermitian or not. To check something is Hermitian, what we do? We do complex conjugation, and we'll check if it is equal to that given thing. But when we are taking complex conjugation, it becomes this. But if we multiply with a, multiply with k, it will become this. So from here, it is clear that it is not closed under scalar multiplication. Is it okay? Okay. So this is not true. Though it is closed under addition, but it is not closed under any scalar multiplication. So this is false. So option C is the only answer. So let us solve question number 8. Up to this, is there any question? If there is any question, please ask. Okay.
Sir,
Yes.
closure under addition like this you are telling, right? So
Yeah.
how to realize that R3 means you are plotting some graph, two axis
Yes.
graph, right? So
Yes.
how to understand that the closure under addition means?
Okay. So let me draw a picture, then maybe it will be easier to understand. So what is the meaning of, what is the geometrically meaning of closed under addition? So suppose this is R2, this is R2. The vector space is V, and we are trying to make a subspace from this vector space R2. So what are all possibilities? So we need to check if 0 is there. So 0 is there means the W should contains 0, this element, right? Then what are the other thing? It should be closed under addition. Suppose this vector is there. Suppose this is a vector which can be written as maybe 1, 2, 3, 1. This is closed under addition. What is the meaning of this? First, let us see what is the meaning of closed under scalar multiplication. So scalar multiplication means you are stretching, right? So you are stretching means you can just stretch to this, or you can stretch means you can make it smaller also, and in the negative direction. For example, just multiply -1 times 3, 1. Then you can see that it will becomes 1, 2, 3, maybe.
Minus
So
4.
yes. So it will be -3, -1, like this, right? So if you scale by all such real numbers, then you can see that this line will be the possible thing, right?
Yes, sir.
So now can you see that this line, all those things, all those vectors are those are closed under addition. If you just pick any two things, for example, pick this vector and pick another vector, then add those two things, what will be the addition?
Sum of these two, sir.
Sum of these two things. So the addition will be this vector, right?
Yes, sir. Yes,
It
sir.
should pass through 0, but I have just said to visualize it. So you can see that it is no, it is closed under addition. But
Okay.
if you pick, for example, just consider the subspace like this. Subset, not subspace. So sorry, just a shift, small shift. Okay. So consider those two lines. First line is this diagonal. Maybe this. This diagonal line. Sorry. Like this, and another line is this x-axis itself. So this is one line, and this is another line, right? Now can you check if it is closed under addition or not? Two lines. So this two line means we are sketching in all those directions. We are not.
Today.
So you can see that this 2, 0. So we are renaming it W2. 2, 0. This belongs to W2, and similarly this 1, 1.
Okay, sir.
This also belongs to W2. But what is their sum? 1, 1 plus 2, 0. The sum will be 3, 1, right? But
Yeah.
where is 3, 1? 3, 1 means it will be 3 and this 1. So there should be 3, 1.
Yes.
It will be the vector. So this vector lies inside W2. Is it true? W3 is
Yes, sir.
this axis union this line. So this vector lies in this picture. Is it true? Is W3 lying inside these two line?
Yes, sir.
Is it true?
Yes, sir. It is true only, sir.
Not. I am not asking if it is lying on in the plane. I am asking if it is lying in this x-axis or
No, no.
this is
No,
not
no.
true, right?
Yes,
So
sir.
so here you can see this W2. This is not a subspace.
Okay, understand.
Okay. You can see that it is closed under scalar multiplication. For example, if you multiply 2/0 with some element, for example, let us choose 4, then it will be 8, 0.
Yes,
But
sir.
8, 0 is also there. 8, 0 will be in the x-axis somewhere.
Yes, sir.
So though it is closed under scalar multiplication, but it is not closed under addition.
Addition.
Okay. So just to visualize this, always remember that subspace, it will look like, for example, in 3D, a subspace will be some kind of plane or a
Yes.
real number or a real number. Subspace of R3, it will be a plane or a real line or a straight line.
Okay, sir.
Okay. Similarly, subspace in R2, it is just a straight line. Either
Okay.
straight line or the whole plane. Because whole
Okay.
plane is also a vector space.
Thank you, sir.
Okay, nice. Nice. So let us solve the next question. Question number 8. Here the subspace W, which is a subspace of R4. So subspace of R4 means it will look like a 4 tuples. So here is a 4 tuples. Another is this, and this is another thing. Then which of the following vectors is in the W? is in W. So if this is inside W or not, we need to check this. So how do you check if something belongs to W or not? So W is a subspace, it is already given, and 3 vectors. So W is spanned by 3 vectors. What is the meaning of this? So let us write anywhere. Okay. Oh, this is not allowed. So what can be done? Let me write in this notation. So how do we copy this? Copying is not allowed, right? Copying this picture is not allowed. Maybe screenshot. Yes, screenshot is allowed. Yes, nice. Okay. So let me paste here.
Sir, R4 how to really visualize, sir?
Okay. R4 you cannot visualize, but you can just generalize this, right? For
Okay.
example, R2, you can go in higher dimension, R3. You start with a point. After that, you just move left or right. Then you will get real number. Now you can move
Up
up
and down.
and down. Then you will get R2. Now you can go in this direction also. Then you will get R3. Similarly, in higher dimensional analog is also possible. Though it
Okay.
is not easy to visualize, but there is something, and we always use those type of things. For example, in computer, you have already used arrays, right? Arrays are also element of Rn.
Okay.
So that's why it is important, and properties of those things it is important. So let us just uh, okay, it is not allowed, but what can be done? Sorry, just add a picture. Sorry. How do we add? Maybe. Sorry, I think this option is not there. So let us write this question 1 1 minus 2 1. So one vector is 1 1 minus 2 1. Suppose this is W1. W2 is 304 minus 1. 304 minus 1. And what is W3? W3 is minus 1 to 5 2. Minus 1 to 5 2. So the subspace is spanned by those 3 things. So W, the subspace is given by equation. W is spanned by those 3 elements. What is the meaning of that? It means W will look like C1 times W1 plus C2 times W2 plus C3 times W3. Right? Where Ci belongs to some real. Now the question is, if that, which option? So first option was this 0 triple 3.
Triple three.
Okay. So the question, if 0 triple 3, this belongs to this space. Question 1. This is option 1. We are considering question number 8. So is it belongs to W? How do we check? So there are several possible ways to check. The most easiest way is to do those matrix operation and check if it is there or not. So how can we check? We just write. So the question is like this: if this can be written as C1 times W1 plus C2 times W2 plus C3 times W3 for some C1, C2, C3. Can we write? If we can, you can give some answer for this, it is true. If you cannot make any answer, then it is wrong. You need to prove that it cannot be made. Okay, otherwise give me some C1, C2, C3. So another way to check it by doing some row, making a matrix and made it to row echelon form. So let us make a matrix A out of this. So 1, 1, minus 2, 1, 3, 0, 4, comma, minus 1, and minus 1, 2, 5, 2. We have just put those three elements, four tuples in rows. And now we'll perform row operations. So first, what will be the first row operation? It is R3 minus 3R1. So 1, 1, minus 2, 1. This is fixed. This will vanish. So it is 0. After that, it is minus 3 times R1. This is minus 3. Then 4 plus 6, right? 10. And minus 1, minus 3. It is minus 4. Similarly, to make it 0, we'll do, sorry, this is R2. This is row 3 plus row 1. So it will become 0, then 3, then 5 minus 2, which is 3, 2 plus 1, which is again 3. Right. Then what can we do next? Just row exchange so that it becomes easier for us. So R2, R3, those two rows are exchanged. So it becomes 1, 1, minus 2, 1, 0, minus 3, 10, minus 4, 0, 3, 3, sorry. It is 0, 3, 3, 3, and minus 3, 10, minus 4.
Minus 4.
Yes, minus 4 is. So after that, what can we do? Just, I'm not writing again, but just 1/3, maybe 1/3 times row 2. Okay. So it will become 1, 1, minus 2, 1, 0, 1, 1, 1.
Second one.
Yes, true.
Again.
And third one will, yes. So instead
0
of,
minus 1.
yes, 0, minus 3, 10, minus 4.
Minus 1.
Yes, you can subtract, you can divide, but I'm not dividing. So now make it vanish. So R3 plus 3 times R4, 3 times row 2, so that it will become. So I am giving a row echelon form of this 0, 1, 1, 1, and it will becomes 0, 0, right? 3 plus 3 minus 3 plus 3, which is 0. Then 10 plus 3, which will be 13, and minus 4 plus 3 is minus 1, right? Now, can you see that this element is there? In some, by some row operation, scaling and addition, can you make this element 0, 3, 3, 3? Some scaling operation, and that is adding those three rows. or maybe scaling and adding, can you make it 0, 3, 3, 3? That is, suppose those elements are, suppose this is W1 dash, first row is W1 dash, second row this is W2 dash, this is W2 dash, and third row this is W3 dash. Can 0333, can you write it as CW1 dash plus C2W2 dash plus C3W3 dash? Can you write it like this? Yes. Can anyone see? So let us try in this way. So first element is 0. So how do you make first element 0? From here, how can you make first element 0? What will be the coefficient of this W1 dash? So if you take any non-zero element, can you get this? Because first element must be 0. What is the possibility?
Multiplication.
You must choose first element to be 0, right? 0 times W1 dash. If you choose some non-zero element, then you cannot produce 0 here, because other thing contains 0 in the first column, right?
Yes, sir.
So first element must be 0. Now second element is 3. How can you produce the second element? So this is done. How can you produce the second element? Can you do some operation? That is, what will be the scaling of W so that it becomes 3? Can you see that if we take 3 times W2 dash, then this element will be 3,
Yes, sir.
right?
Yes, sir.
And moreover, if you just multiply 3 with W2 dash, then everything is matching, right? You can see that 3 times W2 dash, 3 times W2 dash is same as 3 times 0, 1, 1, 1, which is again 0, 3, 3, 3. So from here you can check that this element can be expressed as linear combination of W1 dash, W2 dash, W3 dash. Hence, this can be also written as linear combination of W1, W2, W3. So what is the steps? What are the steps? You just perform row operations, and I have stopped here, but it is better to produce row reduced echelon form. Then it will be more easier to see, because in that case, above entries will be 0, right? Those above entries will be 0. So it will be more easier to check, because then only you need to check those combination. Is it clear? So the what are the steps? Reduce to row reduced echelon form, and now check the desired tuples, desired n tuples, here 4 tuples can be written as combination of rows. So yes, So for example, suppose A is reduced to this answer. Suppose A is reduced to, after some row operations, A is reduced to this one. Suppose A is 3 by 3 matrix and row reduced echelon from is 1 0 0 0 0 0 1 0 0 0. Suppose this is row reduced echelon form of A. Then can you see that? Can you check if 2 3 4? Can you write 2 3 4 as linear combination of rows? Combination of rows. Can you write 2 3 4 as linear combination of those rows? R1, R2, R3. Is it possible? So how do you make this element 2, first element 2? What will you do? Multiply this first row with
the 2.
2. Yes, right. How do you make second element 3? Can you give combination R2, R3? Can you give any coefficient which will make this middle thing 3? You can see it is 0, it is also 0, it is also 0. So can you give me something which will make it 3? Is it possible? So let us see if 4 can be made. Can you make it 4? Last element 4? For 4, what will be your coefficient? You can multiply the second row with 4, right? Okay. 4 times row 2. 4 times row 2 will give you 4. Is it clear? 4 times row 2 will give you 0 0 4. So 2, this is okay. 4 is okay. But this middle 3, you cannot produce this middle 3, right? Because everywhere it is 0. This row contains 0 in the middle. This row is 0. But this row is also 0. So whatever combination you choose for any C, you cannot produce this element. Is it clear that why 2 3 4 does not belongs to this subspace? Because of this restriction, middle rows contains 0. Row reduced echelon form. So this is the procedure. You just reduce it to row reduced echelon form and see if those options can be made in such a linear combination of the given rows. If you can make it, then the option is true. If you cannot make it, then option is wrong. So this is the process of solving this type of problem. Okay, let me put it here. It was for that question. Okay. Maybe a different color border. Okay. So question number 9. So again, we need to check if something is subspace or not. So V is the real vector space of all functions from R to R. Is functions from R to R. Okay. For example, V can contain this polynomial 2x plus 3x squared. This is belongs to V. Or V can contain this sin x. This function is also belongs to V. Any function is there. Now you need to check that which of the following sets is a subspace. So set 1, here W1 is given as all f which satisfies the condition fx square equal to fx whole square. Is it true? So is 0 there? 0 belongs to this space. You can see, let us check for option 1. Let us see fx equal to 0 satisfies this conditions. So if fx equal to 0, then fx square, this is for all x, then fx square is also 0, and which is same as fx whole square for all x. Therefore, the function 0 function is there. 0 function belongs to W1. Now the second thing we need to see if it is closed under scalar multiplication. So let us put fx equal to x. Then f belongs to W, right? F belongs to W1 because f of x square is also x square, which is same as fx whole square. This is true, but let us do some scaling operation. So let 2 times fx. So the function denoted by 2f, it is defined as 2 times fx. So is it belongs to W1? We need to check if this satisfies or not. So 2f x square, by definition this is same as 2 times fx square. Now if you put this thing 2f x whole square, then by definition the inside thing, this is can you just make there is some noise, can you mute your mouth mic? Okay, so 2f x whole square, by definition this is 2 times fx. Now if you make it square, then it becomes 4 times fx square. But our fx, we are checking the condition scalar multiplication. So fx equal to x, we have assumed that. So here it is 2 times x square, because fx is same as f is identity, right? F of x square is x square. And similarly 4 times f of x square, which is 4x square. So from here you can see that this equality is not holding, that this is not true, because it will give 2x square here, and the second thing is giving you 4x square, which are not equal, right? So from here you can see this is not closed under addition, so this option is incorrect. Now the second thing is f0 should be same as f1. So is it holding for 0? So the 0 function, for 0 function, you can see fx equal to 0 for all x. Therefore, f0 equal to f1. This is holding for 0 function. Both are 0. Now, what are the other conditions? That is, if it is closed under addition and closed under scalar multiplication. Are those holding in this case? Given f0 is same as f1. Then scalar is also there, right? f0 is f1. It will means k times f0. This is same as k times f1. So therefore f belongs to w2. Let us denote it by w2. F belongs to w2 will imply scalar multiplication also belongs to w2. So closed under scalar multiplication or scaling, this is true in this case. Now the second thing, the next thing, the final thing is to check if those are closed under addition. So suppose for f this is true, and also for g this is true. G0 is same as g1. So this is true. Now the last thing is g0 equal to g1. Then f plus g0, which is same as f0 plus g0, but f0 is same as f1, g0 is same as g1, but by definition this is f plus g1. So this is closed under addition and closed under scalar multiplication. So we have observed that if f comma g belongs to w2, we have assumed that g belongs to w2 by this, right? If f comma g belongs to w2, this will imply f plus g also in w2. Therefore, it is closed under addition. Since those two are true, therefore this is correct. Similarly, here it is wrong because for 0 function, 0 does not belong to this. For 0 function, if you apply on -1, it will again give you 0. So 0 does not belong to this, so this is wrong. And what is the problem? Again, 0 does not belong to there. So to discard those type of thing, you always check with the question if 0 belongs to there or not, right? Again, because 3 plus f0, it will be 3, but f of 0 square, it is not 3. So equality does not satisfy by the function 0. So this is also wrong. So question number 10. What is the question number 10? It is all n by n matrices. Then which of the following are subspaces of phi? So this is not true. Again, the 0 by 0 matrix, n by n matrix, 0 does not satisfy this condition. So this cannot be an answer. This is wrong. A is invertible. 0 cannot be there. Right? 0 is always non-invertible. So this is also wrong. The next thing here, you can see that for option 3, you can see I cube equal to I. But if you take the scalar multiplication, 2i whole cube, which is same as 2 cube into I, which is 8i, this is not same as 2i. So we have chosen 2i here. We have put a equal to 2i, then we are getting a cube not equal to 2a. So this is also not closed under scalar multiplication. But here you can check that it is closed under addition and scalar multiplication. So this is not closed under scaling, but this is true for all those properties. This satisfies all those properties. closed under addition and closed under scalar multiplication. Hence, this is the right answer. You can easily check. This is similar kind of check. So, okay, we are stopping here. If you have any question, please ask. Is there any question?
Sir?
Yeah.
Sir, that last option you put some E. Can
Yeah.
we use like that? That the ninth question you are using vertical, but here that is on the left side.
Yes. For which option you are asking?
But the notation, sir, that the psi not like that you put right belongs to not.
This thing.
No, sir. Last, go to last.
Last. This.
Sir, last 10th question, sir. 10th question.
Okay. 10th question. Okay, right.
Sir, the last is the all A such that A is invertible like this, na?
Yes.
After that you put some symbol, right?
Yes.
Like this.
So, first thing we'll check how to prove something is subspace. It will be closed under addition and closed under multiplication, scalar multiplication. So, always remember, if 0 is there in the vector space, then the subspace always contain the same 0. So, in the vector space, n by n matrices, 0 is that 0 matrix, everywhere 0. But in the subspace, this cannot be there. Means in this subset, 0 is not there because 0 is not invertible, right? Jayaprakash?
Yes, sir. Yes, sir.
So,
Sir, I am audible, sir.
yeah.
Yes, sir. Yes, sir. I am listening only, sir.
Okay. Is there any doubt?
No, sir. I satisfied, sir.
Okay. Thanks.
Okay, sir.
Okay.
Thank you.
If you have any further question, then please. Otherwise, we may stop here.
Okay, sir. Thank you so much, sir.
Okay.
Sir, will you share these questions in the portal?
Yes, I'll share. I'll upload in a link and it will be shared.
Okay. Thank you, sir.
Okay.
Thank you, sir.
Okay. Thank you. We are stopping.